So next we want to discuss the simple harmonic oscillator. All right. So the simple harmonic oscillator is by far the most important quantum mechanical system. And one of the reasons for that is any like complicated potential, if it's a bound potential, so if say V of X is a bound, is a potential, is a potential, with a local, say minima, or local minimum, I should say, at X equals to X0, then in the neighborhood of X naught, V of X looks like V X minus X naught, right? V of X naught plus the first derivative is 0, right? X minus X naught dV by dx. This term is 0 because it's a minimum, right? Plus the leading term is X minus X naught squared d squared V dx squared evaluated at X equals to X naught plus higher order term. Right? Is that clear?
Yes, sir.
Yeah. So what do we mean graphically? What we are doing is the following. We have some physical system with some kind of complicated potential. So this is X, this is V of X, and you have something like this, right? So here we have, okay, this is X naught, and we can always change our variables to choose that point to be 0. And near the minimum, this potential is approximated by a quadratic function, right? So near the minimum, this potential can be written as half k X naught with an appropriate change of variables. That's basically what I'm saying. And we don't care about some constant value, right? So essentially, with a bit of change of variable, locally, the local Hamiltonian for any system with a local minimum or a global minimum, if it's a global minimum, that's even better. Your Hamiltonian will look like p squared by 2m, the kinetic energy of the particle, plus a quadratic potential term, right? So this is a very, very important Hamiltonian because it captures the small oscillation of the particle around some, stable equilibrium state, okay? H captures the small oscillations of a particle around some stable equilibrium state. Okay? Any questions? All right. So, right. So let me then draw the potential for this guy. So we are forgetting about the the original problem, and we are just looking at the, so this is x, this is v of x, and our potential looks something like, sorry. Okay. This is the potential for the simple harmonic oscillator. Okay. So what is the classical solution? So you can work out the equation of motion, and it's very easy to verify that the classical solution to this equation is x as a function of time is going to be some constant, integration constant, which is the amplitude of the oscillation, cosine of omega of t plus phi. Phi is some phase, which determines how you measure time t equals to 0. And omega is a constant defined by the parameter k and m, square root of k and m. Okay, so you can show this. This is the classical. This is very easy to show. And it's also easy to show, well, the total energy, E, which is the Hamiltonian, the numerical value of the Hamiltonian. Of course, this is going to be, you know, if you have a classical system and this is the total energy, you know, if this is the amplitude A, then whenever the particle is here, its kinetic energy is 0 and its potential energy is going to be total energy. So the total energy of the particle will be half of k a squared, or in other words, half m omega squared a squared. Okay? So this is the classical solution. So quantum mechanically, you know, we want to solve this equation. H psi is equals to E of psi. So this is the energy eigenvalue equation. So if I write it out explicitly, I get H. This is the kinetic term. And then we have a bunch of constants. And then E is the energy minus the potential energy, K of x squared of psi is equals to 0. Okay? So this is the differential equation we have to solve. So for convenience, you know, let us introduce a constant E0, which is half h bar omega. And then the energy is, we express energy in units of E0. Okay, so we express energy as some constant times E0. Okay, so we can now express our, Schrodinger equation in terms of lambda. So we can also show that A, the amplitude, the classical amplitude, you know, which is essentially given by h bar over m of omega. This we can take as a measure of distance, as a unit of distance. And then we say that, well, x is equals to then x prime a. So this is measuring distance in terms of a. So if we use these constants, then our equation becomes m of omega divided by h bar d squared psi dx squared, there's a prime here, plus lambda minus x prime squared, psi is 0. Okay? So then we see that this is just a constant, so we can just, divide by that constant, and we just relabel x prime to be x because there is no x anymore. And then at the end of the day, we get minus del squared psi del x squared plus x squared of psi is equals to lambda of psi. Okay, so this is the rescaled kinetic energy. This is the rescaled potential energy. And this is the rescaled energy, okay, times psi. Well, you know what I mean. Kinetic energy term. Okay. So this has this equation has the form an operator times psi equals to E times psi. Okay. Any questions so far? So this is a problem we have to solve. I've just re-expressed this in a different way. Any questions?
So how does this like help us in other situations?
So this is an eigenvalue problem now?
It is, yeah. It was always an eigenvalue problem, right? Because the time-independent Schrodinger equation is an eigenvalue problem.
Oh, but now it's a simpler eigenvalue problem, I guess.
Yeah, it's just I've just basically set all the. What I've done is that essentially I've taken, I've taken some units which are no more natural, right? Because we have just chosen to measure energy and distance in terms of, we have chosen like dimensionless units for energy and distance.
I see.
Okay? Because we are measuring distance we're measuring distance in terms of A and energy in terms of E naught. Okay? That's what we're doing.